Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 18, Organic Chemistry 2. Today we will continue on chapter 4, Aldehydes and Ketones. We will cover the preparation of aldehydes and ketones and introduction to nucleophilic addition reaction. In the previous lecture, we covered the synthesis of aldehydes and ketones from alcohols, alkenes, alkynes, and Friedel-Crafts acylation reaction. Today we will continue on synthesis of ketones from carboxylic acids. Carboxylic acid in its lithium salt, lithium carboxylate, reacts with organolithium via nucleophilic addition reaction to give the dianion. This dianion, upon hydrolysis followed by dehydration, provides ketones. Show how you would accomplish the following synthetic conversions by adding an organolithium reagent to an acid. Benzoic acid to acetophenone. If we take benzoic acid, reacts with two equivalent methyl lithium, the first one will form the salt. The second methyl lithium will add to form the dianion. We follow that by hydrolysis followed by dehydration to provide acetophenone. We can also get the lithium benzoate first using lithium hydroxide, then add one equivalent of methyl lithium to give dianion, which upon hydrolysis provides the hydrates, dehydration to give acetophenone. Convert phenylacetic acid to 3,3-dimethyl 1-phenylbutane 2-on. So just replacing this part, with tertiary butyl. So what we have to do, react phenylacetic acid with two equivalent tertiary butyl lithium will lead to the formation of the lithium salt, then add to form the dianion, which upon hydrolysis give the hydrate, followed by dehydration to provide the target molecule. Synthesis of aldehydes and ketones from nitriles. Aldehydes and ketones from nitriles. Nitrile, nucleophilic attack by nucleophile, addition to form this anion, protonation provide imine, hydrolysis of imine in acidic medium give iminium ion, attack of water on iminium ion, led to the formation of this oxonium, minus H plus H, so H will move from here up to the nitrogen, then this lone pair will go to form a double bond, kicking ammonia out, deprotonation, provide the ketones. If H minus is H minus, that will be aldehyde. If nucleophile is carbanion, that will be ketone. So, reacting the nitrile with aluminum hydride can reduce nitrite to the corresponding aldehyde. Diisobutyl aluminium hydride, abbreviated by DBALH or I-but2ALH, is commonly used for reduction of nitrile. So H- will add to form this complex, which upon hydrolysis provides aldehyde. This is the structure of the diisobutyl. Here is the isobutyl, diisobutyl aluminium hydride. A Grignard or organolithium reagent attacks a nitrile to give the magnesium salt of an amine. Salt, which upon hydrolysis provides ketone. Synthesis of aldehydes from acid chloride. You replace Cl with H. To do that, you use lithium tri-tertiary butoxy aluminum hydride. It's a milder reducing agent, reacts fast with acid chloride than with aldehyde, reacts faster with acid chloride. So you take the acid, you react it with thionyl chloride to form the acid chloride, treat that with lithium tri-tertiary butoxy aluminum hydride, you get the aldehyde. If you use carboxylic acid, you reduce that with lithium aluminum hydride, you get slow reduction to aldehyde but fast to an alcohol. So you get always alcohol as a product. But using lithium tri-tertiary butoxy aluminum hydride, you transfer from acid chloride to an aldehyde. To get ketone, acid chloride react with lithium organocuprate, Gilman reagent, to give a good yield of variety of ketones. So acid chloride with R2 cup lithium, you get ketones. With Gilman you can do that, but with Grignard, addition of organomagnesium to an acid chloride is fast process, and again it is fast process with the ketone intermediate, so you get tertiary alcohol using organomagnesium, you get tertiary alcohol from acid chloride, while Gilman reagent with acid chloride provides ketone. Synthesis of aldehydes from ester. If you'd like to transfer ester to an aldehyde, means that you replace OR prime with an H. How you do that? Again, you use the diisobutyl aluminum hydride as a reducing agent. You get this complex, you add it to water, work up, you get the aldehyde. Again, methyl butanoate or methyl, common name methyl butyrate, with diisobutyl aluminium hydride as first step. Then you add water later on in the reaction. You get butanal, common name butyraldehyde. Reactions of ketones and aldehydes. We have covered that, but we have to shed the light on a little bit more. Nucleophilic addition. The carbonyl is partially positive in here, partially negative in here. So nucleophile will attack, giving O minus alkoxide. Then proton transfer, H from solvent of the reaction mixture, from the workup later on, you get the H, and so it's nucleophilic addition. You added nucleophile, and on the X, O, you add an H. Examples, we have already covered Grignard reaction. When Grignard reagent as a strong nucleophile attack on the carbonyl, this CH3 takes 2 electrons and move toward the partially positive carbon, giving salt. Upon hydrolysis gave alcohol. Reduction of aldehydes and ketones with hydrides, like sodium borohydride, H minus will attack on the partially positive carbon, provide alkoxide, which upon protonation with solvent like water or alcohol furnish alcohol. In case of weak nucleophile, such as water and alcohols, we can activate the carbonyl under acidic condition. So if we add in the reaction mixture few drops of an acid or crystals, what will happen? First, lone pair on oxygen will catch up this H plus, give this activated species. The carbon will have a positive charge here, resonance contribution, so it's clear for the nucleophile to attack, even weak nucleophile, to give the addition product. In most cases, aldehydes are more reactive than ketones. Two factors play a role: electronic effect and steric effect. For electronic effect, the polarization of carbon oxygen is in this way, right? However, we have R donating group. In aldehyde we have one. On the other hand, in case of ketone, we have two groups pushing on the carbon positive charge, decreasing the density of the positive charge, right? So the aldehyde will be more reactive. What else? Around this carbon in aldehyde, there is one substituent. On the other hand, in ketones, you have two groups, sterical, especially if it's the bulk group. Okay, so steric effect. Sodium triacetoxyborohydride is a mild reducing agent that reduces aldehydes much more quickly than ketones. So here we have ketone and aldehyde in one molecule, 3-oxobutanol. You treat that with sodium triacetoxyborohydride in acetic acid. You reduce only the aldehyde functionality and you keep the ketonic function as it is. And you get 4-hydroxybutane-2-on. Draw a complete Lewis structure for sodium triacetoxyborohydride and propose a mechanism for the reduction of an aldehyde by sodium triacetoxyborohydride. Well, this is the Lewis structure. It resembles the same as the borohydride, BH4 minus. Here we have the structure a little bit deformed tetrahedral. The reaction here, nucleophilic addition, hydride, attack, forming alkoxide, protonated by the H of acetic acid to form the alcohol. Show how you would accomplish the following synthetic conversion from benzaldehyde to benzophenone. This connection approach, benzophenone, you can obtain from diphenyl methanol. Then you get this secondary alcohol from aldehyde and Grignard. You got in here. Reacting benzene with bromine iron 3 bromide, you get bromobenzene. React with magnesium in dry ether, you get phenyl magnesium bromide, which adds to benzaldehyde to give the salt. Hydrolysis with water to get diphenyl methanol, which upon oxidation with chromic acid you get the benzophenone. See you next lecture.